Hi everyone. So in this video we're going to learn about the isoelectric point of triprotic ions, that is aspartate. So one of the example of triprotic ions is aspartate. Don't get confused. I'm going to go step by step so that you don't get confused. So let's start with the very first definition, that is what exactly is an isoelectric point. So an isoelectric point is that particular pH at which a molecule will have two charges. It will have a one positive charge and then one negative charge, which will lead to a net charge of 0. So that particular pH is known as the isoelectric point. I'll be showing you how. Suppose this is an amino acid, right? So in an amino acid there are two possibilities. The first possibility is that this is the alpha carbon. So this particular carboxylic group is also known as alpha carboxylic group. This is attached to alpha carbon, so this can be also known as alpha amino group, right? So there are two possibilities. The first possibility is that this can lose a hydrogen ion and then it can have a negative charge, right? So it is undergoing deprotonation. We can use this term as deprotonation, right? Another possibility is that this being NH2, it can gain one hydrogen ion, right? So now what will happen, instead of NH2 this will become NH3. Now this will have a positive charge. This particular process is known as protonation. So the reason why this is donating an H plus is because it is an acid, and the reason why it is accepting an H plus is because it is a base, right? So now let us see other things. Okay, so one of the most important thing that we need to understand is what exactly is pKa₁, pKa₂ and pKr value, right? So pKa₁, as I already discussed in my previous video, pKa₁ is actually the acid dissociation constant of alpha carboxylic acid. So how quickly does the alpha carboxylic acid of the amino acid loses its hydrogen? That particular thing is known as pKa₁, and it is associated with COOH. COOH, right? So I can see that pKa₁ is this value where this carboxylic acid will lose its hydrogen, right? So this is pKa₁. Now another one is pKa₂. So pKa₂ is the acid dissociation constant of alpha amino group. So I can see that this is alpha amino group. So how quickly does this amino group receives, or it receives a hydrogen ion or donates a hydrogen ion, it depends upon that. So this is actually the pKa₂ value, right? Another one is the pKr value. So the pKr value is actually the acid dissociation constant of the side chain or the R group. Now you must be wondering, what exactly is this pKr value? So if I just give you an example, for example, if instead of R it was CH2 and C double bond OH. This is aspartate or aspartic acid. Now, if a carboxylic group or an amino group is present in the R group, so this is the R group, right? This is the R group. So if a carboxylic acid or an amino group or any kind of other functional group is attached to this particular carbon, alpha carbon, which will be able to donate or accept a proton, that is a hydrogen, which will be able to donate or accept a proton, that is the hydrogen, that particular value is known as pKa value. So the particular pH at which this COOH loses its hydrogen is known as pKa₁. The particular pH at which this NH2 loses its hydrogen or gains a hydrogen is known as pKa₂. And then when this R group loses its hydrogen or accepts a hydrogen, it is known as pKa value. So I hope you're clear about pKa, pKa₁, pKa₂ right now, right? So now let us see. Okay, so last example we talked about was of glycine, right? So glycine, as we can see, the structure of glycine, let me draw the structure of glycine. So glycine was very simple. This was H, right? So in glycine, when the pH was around 2.34, this COOH donated its hydrogen. And then when the pH was 9.6, this NH2, this is NH3 actually, this is plus sign. So this NH2 had donated its hydrogen, right? So the reason why glycine is called a diprotic amino acid is because it has only two groups which will be able to either accept or donate hydrogen. So the first group is this one, and then the second group is this one. If you're not able to catch up what I'm trying to say in this video about glycine, I request you to go back to my previous video about zeta ions and then watch that video and come back so that your basics are clear about it. So I've just added a new word out here, that is diprotic amino acid. That is the only word that I've added out here. Okay. So now we understood what exactly is a diprotic amino acid, right? A diprotic amino acid is an amino acid which has two groups which can either donate or accept a hydrogen ion. Now in triprotic amino acid, what happens is there are the R group of that particular amino acid also contains a functional group that might be able to donate or accept a carbon atom. So I just showed you the structure of aspartate, if you remember. The reason why I showed you the structure of aspartate was because I wanted to show you how does this is actually a triprotic amino acid. So this is the first group that will be accepting or donating a hydrogen. This will be pKa₁. This will be pKa₂, which will be either accepting or donating a hydrogen. And this particular R group also has a functional group which is capable of either accepting or donating a hydrogen. So can you see there are three functional groups which is able to either donate or accept a hydrogen. Therefore, it is known as triprotic ions, right? Triprotic amino acid, we can say that, right? Now let us go back to what I was trying to say. Okay, so triprotic ions could be, the triprotic amino acid could at least contain these 4 groups. It could be a carboxylic group, it could be an amino group, it could be a hydroxyl group, or it could be a thiol group. It all depends, it all depends upon like what amino acid we are talking about. All these functional groups have different pKa values. That means if a particular amino acid is containing COOH, then they will have a particular pKa value where they will be losing or accepting a hydrogen. If a particular amino acid has NH2, this will be different from COOH, OH and SH. So every other group will have their own unique pKa value where they will be accepting or donating a proton, that is a hydrogen, right? So now let us see how do we calculate the isoelectric point of a triprotic ion. So we already know how to calculate the isoelectric point of a diprotic ion in terms of glycine. So that is the same formula that we're going to use for all the diprotic amino acid. But in case of triprotic amino acid, we have a different formula. So we'll look on it. So let us see here. We all know that the pH in this one, the pH is very low, right? The pH is very low. That means hydrogen ions are more in number, right? So I can write that more hydrogens, right? Now, when there is more hydrogen, what will happen? The COOH will remain as it is. But what about NH2? This is actually NH2, right? So this is actually NH2. What will happen now? When the hydrogen ions are very much higher in number, there is a possibility that, this NH will be able to gain a extra hydrogen and then have a positive charge, right? This is a possibility because the hydrogen ions are very much high in number, and then NH2 will be able to accept a proton and gain a positive charge. So the charge out here will be +1, right? Now let us see over here. Let us see in the second one. We have NH3, right? We still have NH3 and then we have a plus. So where is the pKa value that we need to understand? Okay, so 1.99. Because I'll just take this above. Okay, I'll keep it here. Okay, so this particular amino acid that we're talking about is actually aspartic acid. So I hope I was clear about it, because I told you in the first place that this structure is aspartic acid, right? So when aspartic acid was under high pH, what was happening was it suddenly started to donate its aspartic acid. It suddenly started to accept hydrogen, right? So now let us see which is like the next value. So the first value is pKa₁. So pKa₁ value is where the carboxylic acid will lose its hydrogen ion. We know that, right? So now let us see what happens over here. Oh my goodness, this is like really big. I'll just make it 2. So the carboxylic acid will now get a negative charge, right? And what is the charge of this particular ion? what is the charge, of this molecule? What do you think it will be? This will be 0, right? Okay, so now let's go to another one, that is the other value. So now we have another value, which is pKa value. So pKa value is less than pK2 value, so we have to take consideration of pKa value first. So now what will happen, what has already happened is there is an NH3 over here, and then a positive charge already over here, and then the COOH has already been lost, and then there is a negative charge over here. Now what will happen is pKa value, that means, what is pKa value? pKa value means this R group will now lose its hydrogen ion, right? So now let us see how does it look like. So this hydrogen ion is lost from the COOH, right? So now what will be the charge of this molecule? Since plus minus will balance it out, then it will be -1, right? I hope you are clear with what I'm trying to say, because why did I took this value first? Why did I took this value first? Because this is smaller than this one. So I'm going like, in a sequence manner. So first I did this because this was like 2, then I did this because this was 4, and then did this because this was approximately 9.9. So I'm going like a stepwise. Now let us go back to another one, the last one, that is this one, right? So now what will happen is we already finished doing the carboxylic acid. The first alpha carboxylic acid has already lost its hydrogen ion, right? And then the other R group carboxylic acid has also lost its hydrogen ion. Now the turn is of amino group, right? Alpha amino group. So let us see now what happens when we take off the charge. So this was negative, this was also negative. What about this one? This was NH3 plus, right? But then now NH3 plus has also lost one hydrogen, because it has reached to this pK2 point, right? So now it has also lost one hydrogen, therefore now it will be NH2, right? So what will be the charge of this molecule? This will be -2, right? So are you able to understand what I'm trying to say? Okay, so now let us calculate the isoelectric point of aspartate. So we already know the values, right? We already know what are the values. So we're just gonna take these values again, and then we're gonna see how do we calculate the isoelectric point. So the formula will remain the same, of similar to glycine. So the isoelectric point of aspartate will also be taken two values. Just a minute, I'll just show you. Okay, so what are the two values that we're going to take? So we must be wondering what are the two values that we're going to take of aspartic acid that we will be considering in the isoelectric point. So we have to take the value of this isoelectric point. This is the isoelectric point, right? So this is the isoelectric point, and we have to take this value and this value. So can you tell me what value is this actually? This is actually the pKa₁ value, right? And then this value is the pKa value, right? So we have to take consideration of the the values which are right and left to the isoelectric point. So this one and this one. So let us take now the isoelectric point. Okay, so as I told you that I'll be taking pKa₁ plus pKa value, and then I'll divide it with 2, right? So let us just see how much it will be. So the isoelectric point of pKa₁ is 1.99 plus pKa is 3.9, right? Divided by 2. So this is approximately 2 plus 4, that will be 6, divided by 2, and it will be 3. So it will come something like 2 point something. That will be approximately to 3. So this is the isoelectric point of aspartic acid. I hope you were able to understand, why we were talking about diprotic and triprotic amino acid, because it plays a very important role on how are we going to calculate the isoelectric point of those amino acids. So if you like this video, please share, like and subscribe, and then I hope you understood my today's video.